Hello, welcome back. This is season 2 of Extremely Live Science, and I think we're good. So we're back in the office as well. You can see behind me. Why am I a little bit out of focus? You can see behind me. Well, I think my connection is not great, but you can see. Yeah. So right now, this was. Okay. This is now season 2. We have a new project. And I'm gonna be presenting back in the office. So for I generally mention much about my private life, but for the last several weeks I was solo parenting, so there's a strong echo. Yes, let me just move down the volume a bit. I think this might be a bit better. I will also speak a little bit less loud. The last few weeks, so I was a little bit solo parenting, and which means that it was a bit hard for me to do the stream from the office, but maybe for the acoustics is not great. Although I have a much nicer setup because I have the multiple monitors, whilst at home I only had one monitor, which was So I hope the echo is better now. I've turned down the volume a bit, and I'm also making a little bit more of an effort on how I speak to speak in a more natural voice. It's always a little bit a learning experience. I think during COVID we learned when we started doing a lot more things. A lot more things in the streaming and recording, that there's a bit of I'm talking by myself in an empty room. So if someone were to see me, I would come across as maybe not talk. It's a bit. You have to somehow tell yourself that there's actually an audience there somehow, and have that and trigger that in yourself that you want to communicate to someone, as opposed to just being by yourself. I don't know if that made a lot of sense. Anyway, so today I wanted to present this new idea that we had, or that's been a little bit of a brainstorm between myself and several other people. Which is let me see if I can set this up. So. If I can set this up, so how do which is to use the apparent number of pseudogenes in the genome to estimate the quality of the genome. And how we do that is that we okay. Let me first maybe. First, maybe let's see if this works. Let me just. I'm trying to. This is. Okay. Sorry, I forget. I'm trying to set up something which sometimes works very well and sometimes doesn't. Sorry about this. How do I do this? Give me a second. Okay, yeah, this is what I wanted to show. So I basically have the here, and then I can draw, and you will see it. So if I draw it like this, you see it, right? So this is what I wanted to do. So this is it. So what we have is we have a genome, And here, so we have here ATC. Right, this is the genome, which maybe comes from a metagenome. So in this case, it's a MAG. And this genome, it's going to have sometimes some errors. And with Oxford Nanopore technology in particular, or Oxford Nanopore, I mean, we're becoming really, really big fans of Oxford Nanopore. I mean, we're using it; it's great, but sometimes it has little errors. For example, maybe here you see there's a double C. Let's say it's GCCT. Sometimes maybe it will give you an extra C in there, or sometimes it will say there's only one C. So you have these very small errors, these indels, and what this means is that, for example, let's say that this was a gene, right here, ATC. This is the start codon of a gene, and I don't know the genetic code, but you have here the codons, and eventually you have a stop. When you have these very tiny errors, so for example here, let's say it gives you it misses the C, right? So in the original genome, there's the codon is CT, let's say A, but because it doesn't have the C, it's gonna give you this T. So now you have a frame shift, because when we read the gene to go from gene to from nucleotides to amino acids, from nucleotides to protein, we read it by trees. So we read it by these triplets, these codons. So if there's even a small error, now everything after that is going to be wrong, because now instead of CTA, it's going to read TAT, which is a completely different amino acid, and then sooner or later we are going to run into a stop, which is a false stop. Sometimes I think the expression I see in the literature is premature stop. So what we see is that we go from we were going to see a shortened protein and a protein that is correct at the beginning and then gibberish after a certain point, because once you have a frame shift, there's nothing makes sense. So if you have a SNP, so if you go from if you have a point mutation where instead of an A, somehow the system gets confused and thinks it's a C, that's going to change that codon. Sometimes it doesn't even change the codon, but even if it changes that codon, it changes one amino acid in the middle of the protein, and the rest is okay. And many times that's actually completely irrelevant. Biologically, the biophysics, the protein with the 1 point mutation is going to behave exactly the same. However, if you have this premature shift, if you have this frame shift, you end up with gibberish, and now then the premature stop. So this is what we think happens, and this is what we think happens when we have this frame shift. And so what this is going to show is that this is going to show up with here this longer gene, this gene in, so let's say this is in the real genome, you have here some coding sequence that codes for something, for for some function that's functional, and in your genome with the error, it's going to look as if it's a pseudogene, because it's going to look as a non-functional variation of the gene. But in this drawing, this is an artifact. So it's it's an apparent pseudogene. Or as I said, it's a pseudogene, right? It's something that looks like a pseudogene, but it's not a pseudogene. It's just so most of the tools that we have nowadays to look at how good MAGs are or how good genomes are work by looking at individual genes, right? So they find, I think this is true. There might be exceptions, but if I'm thinking, for example, CheckM and CheckM2 actually work very differently internally, but they both look for the genes, and they so they call genes. And here we're mostly focused right now on protein coding genes. So they call these protein coding genes, and so in CheckM1, would look for these single copy marker genes. So single copy. And then in CheckM2, it's actually it's a slightly different model, and it's so the idea in CheckM2, or at least the way my intuition is that, so we know from a lot of genomes that genes come in a group. So if you have gene A, you often have gene B as well, and if you have A and B, often you have C, because A, B, and C form some sort of complex or a function together somehow. And so if you see A, you are also expected to see B, and so if you see A and not B, that's a hint that you are missing B, right? And so my understanding is that CheckM2 comes from this intuition, and then if you take this intuition to its logical conclusion, then give me a second. I think I'm not sure this makes much, but I'm just going to clean the camera here. So if you take this to its not logical conclusion, but if you operationalize this into a tool, then CheckM2 is one of these operationalizations. So what happens if you start having pseudogenes, right? If you start having pseudogenes, so CheckM2 is learning, implicitly learning. It's a machine learning system. It's a little bit hard to know exactly what it's doing, but it's implicitly learning these connections between groups of, let's say, pairs of genes, to simplify the drawing. So it learns that A goes with B, and that C goes with D. So if you have pseudogenes, or let's say apparent pseudogenes that deal, so that these things here disappear, now this will be a missing. So this will lead to lower completeness, and in this case, since these things are more or less random, also it leads to lower completeness. And I will probably be able to show this, not today, but maybe at some point maybe next week. So we first saw this, and this was one of Ana Cusco's data, and where so if we look at the completeness, of MAGs, from long read sequence only, and then the same MAG long read sequence plus Illumina, sometimes made no difference, but sometimes it made a big difference. And so there was a big gain in completeness. And this was, oops, sorry, I somehow messed this up. Completeness, oh yeah, I guess my complete. And this was after this polishing step. And this was at first a little bit surprising, because polishing, so when you polish, you are going back, you are taking the sequence you have and maybe making small corrections. So here we were seeing things go from, say, from 80% complete to 90% complete. So this was, so we have 10% more genome. But the polishing doesn't add 10% more sequencing. So the polishing only adds very small changes. So the genome, if it was say 3 megabase pairs, before it was still 3 megabase pairs, it was not 3.3, so we were not getting 10% more genome. So what we think we were getting is we were fixing these, and in some examples we could see that this was exactly what was happening. So there was some things were getting called as pseudogenes in the original, and then after polishing they were fixed. So so there's so what's happening? So this was the, so we have a genome with a gene. Because long read sequencing is not perfect, it introduces these small mutations, and this leads to a frame shift, and now we have a pseudogene, but it's not a real pseudogene, it's just an apparent pseudogene. And so this apparent pseudogene shows up as lowered completion in CheckM, and so when we fix this, the completeness goes up by a lot, even though we're not adding new sequence when we do this polishing. All right. So here now a couple of questions. So one is, can we take this a bit further? Can we actually operationalize this into a tool? So because if apparent pseudogenes are show up when you have indels, can we then go from an overabundance of pseudogenes to an estimate of how good the genome is? Can this be a fairly agnostic way of checking how good the genome is? Fairly agnostic in the sense, it's not, there's some need for reference information, but not so much. We don't need to know the exact gene sequence before. We just need to know, oh look, this gene category, hand waving a bit, this gene category is normally 300 amino acids, and in this genome it seems to be 200 amino acids. So that would be that would be one way where, so that would be one thing. Can we, so this is one of the goals of season 2, is can we write a tool, takes in a genome and spits out, oh look, I estimate that the indelness, the quality from this point of view is 89 out of 100, right? So there's a lot of hand waving here. But there's also but before we get to that, there's another question that we need to answer is, would this even add something? Because as I was showing, CheckM, both versions actually seem to pick up some of this in a very indirect way, right? This is a very indirect way. I mean, I think a lot of these tools, CheckM, and Junk, etc., these are still very much Illumina era tools, and in the Illumina era, the problems we really, we're still in the Illumina era as well, obviously, but in the Illumina only era, what most of the time the mags were wrong because the binning was wrong. So genomes were not complete because they were missing contigs. So so this is during the binning step we didn't put the right contig together, or for some reason that contig that region of the genome could not be assembled. And we know, and I'll post we know that, for example, things like the 16S genes are often not assembled very well because they're often the worst case scenario for assemblers. You have many copies of the same sequence that are almost but not exactly identical. So this means that for assemblers this is the worst case scenario, because you have these. You have a lot of the assembly graph just looks very messy, where you have a lot of commonality and then small changes. So it's not gonna assemble those regions. So it's not gonna assemble certain types of mobile genetic elements. And so during the Illumina era, these were the biggest problems. That there are some regions that don't assemble well. And then during the binning we might put things together incorrectly. However, if we have a contig, those contigs tended to be quite perfect, quite very close to maybe some very small point mutations, but even that with a modicum of depth, that was very rare. So the problem was fragmentation, and both that the bins were not complete and that some things were just not assembled correctly. In the long read, in the Oxford nanopore era, we start to have this other category of mistakes, which is indels, and maybe this is a problem that's slowly going away with better and better nanopore reads. It's also, we know this, it's also a problem with lower depth genomes. So if with a modern nanopore, if you have enough depth, sorry, that's hard to pronounce. If you have enough depth, then it becomes the sequence is quite good even without any extra polishing from Illumina. But that actually is not a solution for microbial communities, because in a microbial community the long tail is, for all effective purposes, infinite. We are still so far away from sequencing everything that we will always, at least for the foreseeable future, we will have low coverage genomes. So if you increase the coverage, you get a little bit further down that curve where you're sequencing the smaller, the lower abundant community part of the community, but you are nowhere ever close to sequencing everything. So you always have low abundance genomes. Anyway, so this is the setting. So can we find a good can we operationalize this notion? So when we have indels, we end up with a parent pseudogenes. So I'm going to use this nomenclature. So a parent pseudogene is something that looks like a pseudogene in your genome, but it's not a real pseudogene in the original genome, in the actual physical genome. And as I posted, and there's a message in chat as well about, there was a manuscript from Julian, right? Which, thank you, Justine. So this is now apparent. Yeah. So this is a paper from just very recent, making this point that there are many pseudogenes in microbial genome assemblies that are actual genes, and an inflated number of pseudogenes is indicative of poor overall assembly quality. So basically, this last sentence is the impetus for what we're doing here. So we are going to try to turn this last sentence in there. Actually, I should write these authors just to let them know we're doing this. This last sentence here is our impetus for the. I'm going to post this in chat. This last sentence here is the impetus for our project, which is can we then go for inflated number of pseudogenes? So, right, because we also don't, all right. So some intuitions here. We don't want to just count. So there are real pseudogenes. So that's important, right? So having a pseudogene does not mean that your genome is bad. So having too many pseudogenes, whatever that means your genome is bad. So you have these, apparent pseudogenes or artifactual pseudogenes. So we're going to be exploring a few ways of trying to understand that. So that this could be. So this could be, for example, do we have does it look like? So we have here start, and then stop. If this is if there's an indel here, what we would expect is that up until here, well conserved, and then gibberish. So we can ask. We can ask this question, is the start of the gene very well conserved? So this could be one. We could ask, so start or beginning of the gene, start well conserved. We could check whether is it possible to fix. So can we fix it? Right? So this is one intuition. The other one would be, so if, let's say we have this sequence here, gene, and now, so we have a particular sequence, and let's say for some, for the sake of argument, this is 300 amino acids. And now we do some sort of annotation. Sorry about this. We do some sort of annotation, and it's part of some orthologous group 1, 2, 3, 4. It's a 4. But in that orthologous group has many genes that are 500 to 600 amino acids. Okay, so this would be an indication. So this would be an indication that okay, this is a truncated form. So this would be, say, two ideas to explore. The category, in this sense, the orthologous group for this gene is much longer, normally much longer than our version. So this would be So this would be an indication. Before we get to all of that, and now I think I've introduced the project. That's your time. We introduced the project. We're halfway through. Fixable how? Yeah. So here fixable. Yeah. So ideally, so we could, if we detect that the start, there's a point in. So if the alignment of the gene looks like the start aligns very well, and then there's a break, and it's gibberish. Can we restore the Can we restore the frame? Is there a point in that gibberish where we could potentially add a 1 or 2 amino acid, or 1 or 2 nucleotide insertion / deletion, and then everything would look good again. There's obviously a risk of overcorrecting. There pseudogenes do exist. Not all pseudogenes are pseudogenes, but this is possible. And so this is, but as I'm putting it here with some question marks. All right, so now I want to start, and I'm going to start with some simulation. Let's go do the following. Let's go find a good genome, and then let's write some code that adds indels. So we have a mutated version, and then we feed that mutated version into checkm2 and see how checkm2 does. And then we can also feed that mutation into other tools. So for example, when we were working with Anna, one of the things we did, and this is very dumb, but it is to just look at how long the genes are, and so how long our genes on average, and and we were comparing these, again comparing just the Oxford nanopore only to the Oxford nanopore plus Illumina, and so if we did just how long the genes are on average, and sometimes we would see that the same thing in the low coverage when we add, sorry, actually this is an incorrect representation, but when we add Illumina, genes become longer, and obviously the problem is some genes are just longer, and so we cannot just look at just looking at the individual, just looking at the average length. It's not going to work very well. Maybe it works well. Here we are comparing two different. If you're comparing two different versions of the same genome, because but if you're comparing completely different genomes, maybe some taxa just have smaller genes, or just have an overabundance of small genes. So we know, and we have other work on looking at small proteins. That's actually one of our big interests. Some taxa just seem to produce more small proteins. So in that case, having small proteins is the correct thing to do. But so just having the length of the genes is an indicator. So here, here the idea would be, okay, instead of looking at all the average length of the genes, we would look at the average length of the genes within their orthologous group. Okay, so I'm gonna. So this is the first step. Is first step. I can spell first step. Is simulation. Okay. All right. So I'm gonna put this aside. I'm gonna go and all right. Let's start. I'm gonna start from scratch. I am gonna make, and for reasons, I'm gonna call this sardine. And actually the reason is that, so we have this tool called Macrel, which is and Macrel actually stands for something Macrel stands for something, which is metagenomic AMP classification and retrieval. But Macrel is also an old spelling of mackerel, the fish. And sardine, spelled with a Y, is an old spelling of sardine, the fish. Also, as far as I can tell, there's no other existing tool that's spelled like this. And so we will. So I'm going to call it sardine. What is the smallest genome for which this general approach should work? I am interested. Yes, viruses are probably really complicated to do this, because viruses are just viruses are just weird. Viruses are. It's really very very interesting, but they're also just weird. So I don't want to. I don't want to comment about. It's a good question, something to keep in mind for the future, but not sure I want to commit too much at this point. It's very, it's an interesting question. Let's put this on. All right, let's go find the genome. Let's go find the genome. Go find the genome. Then I actually wanted to see it. Okay. There's no. How do we spell it here? I sometimes say it's better to just call it E. coli because you don't have to spell Escherichia. Oh, but okay. Okay, maybe it's not. Okay. Well, progenomes is being a bit slow. I'm gonna set up the same structure I had last time. So I'm going to create the nodes. I'm going to create a. We're going to create source, and probably at some point in the near future we will have a repository for both the tool and the repository for the benchmarking of the tool, and these are separate things. So one will be the tool that we want people, if this works, first we need to make sure it's going to work. But if it does work, we'll have a tool that we want people to download, want people to use, and then there's another repository where it's not about people using it, it's about can we show that it works? Can we add? So spec-i v420. Okay. Yeah, this is the. Okay. I'm going to start with this one because I'm going to say that this one is probably a very very good, very strong genome. It's probably one of the. So let's just download. Okay, we'll download it in a second. Okay, copy it. Okay. We're going to create. We're just going to. I think we're going to be using all of these things. Requests. Is there something else we're going to use? When we're going to use. Is it check M2 like this? Oh. Okay, so. Okay, yeah, this is very good. So chat's saying that Boolean, right? They use figure S1. Okay. Okay, yes, exactly. So they are looking at some E. coli strain, and yes, and they see some frame shifts. Yes, and when you have a frame shift like this, what are these homopolymers? So homopolymer is just a fancy word for GG, many of the same in a row. and sometimes it becomes very difficult to distinguish. This is a 4 Cs from 5 Cs or 5 Gs from 6 Gs. This is, I believe, this is a major source of errors in when using Oxford Nanopore. So okay. All right. So we're good here. So we're gonna use CheckM2 Prodigal. Probably actually. Prodigal. All right. Let's start here. Probably let's start here. And at the same time, make this. I'm just gonna put everything. Okay, CheckM2 does not exist. Oh, is it? Okay, CheckM2 require. All right, so let's stick with Python 3.9. Just stick with Python 3.9. Okay. No, not a simple file size, but sorry, CheckM. Is there? Okay, at some point. Okay, let's do it. Okay, so in that case, I am not going to install CheckM2. We will deal with CheckM2 later. Maybe we need to install it in a separate environment. Okay, right. So make this. Okay. 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 It's not bad, but it's actually wrong. So, yeah, it's not bad. Oops, sorry. sorry. Okay. Yeah, this is. Okay. Okay, I just want to. We might reorganize this a little bit. Stream. We might reorganize this a little bit later, but for now this should work. Okay. All right. Okay, so I'm going to ignore all jug data directories. All right. Genes. Yeah, I'm gonna copy. Yeah, I'm gonna copy. Yeah. Oh, this is pretty old. I don't know. This has not been my email for a while. Okay, so I'm just force of habit. So I'm gonna. So all right. So there's a lot of, sorry about that. It's just a lot of boilerplate here. Just a lot of boilerplate to create the repository. I will immediately after this I'll push it to a public repository. And I will, and now I will add right. I'm sorry. Yeah, so I just apparently it downloads it as a compressed file, so we're just double checking that. Yeah, this is correct. Yeah, I could have fixed this in another way. In this case, it was just a bit easier to completely redo it. Okay. Okay. Right. So. Okay. Right. So. So let's play around a little bit with. Let me just check time. Okay, yeah. So we're running out of time. So yeah, we're running out of time. So maybe we stop for now. I'm just gonna commit the nodes. Start up. I'm gonna add here a note. So today is the 14th. Problem. Okay, and then I'm gonna put. This is a very fundamental paper for this. This is a sort of paper that I actually really like. Something it's at the same time very simple. There's no shade on the authors, but something that in principle could have been published 10 years ago. But it's one of these things. Until they published it, actually, nobody else had published, and it's very it's very nice, very very clean. Just I mean I really like this type of paper. It's just very nice. Yeah. So I'm gonna put this here, here, and reference. I should also check him too. Alex. So I'm also. I guess right. Alex sits. I'm not sure if he's already in, but Alex sits over there, by the way. So put this. So obviously another very important and very nice paper. All right, so startup. Yeah, and the environment. Okay. We did today. Okay. So with that, I'm gonna wrap it up now. I will, partly also because I'm back in the office. It doesn't mess up. I will record a recap. I had stopped doing that, so partly because I would record this and then I'd have to rush to the office, and then it was a little bit harder to fit everything into the schedule. So right now this is less of a problem. So I will post the repository, make it public just after the stream. I don't want to show my private repositories because everybody else's work as well. I'll do that immediately after the stream, and I'll post a recap, and I'll post also on the mailing list. So with that, thank you very much, and I will see you next week.